So in this video, we're going to talk about Shor's algorithm, or we're going to sort of lay the groundwork to actually understanding this algorithm. And in order to do that, we have to first talk about the quantum Fourier transform, which is like a very neat operation you can do to a quantum state to learn something about its like underlying patterns. And this whole idea comes from like the classical version of this, which is what we're going to focus on in this video, which is the discrete Fourier transform. And this thing is like defined mathematically over any particular group. But we're going to focus on a very simple case where the group is like all of these bit strings of length n, and the group operation is this XOR function, or like addition mod 2. And the reason we're doing this is because then we get to define this thing in terms of Boolean functions, and we'll see like a very simple case of this much deeper theory. And we'll also see that it's like this transformation is something we've already studied. In particular, it's like exactly the Hadamard transform, which is pretty interesting. But then in later videos, we're going to like actually generalize this thing to, or not generalize, but go to a different group where the group is going to be the integers mod n, like with normal addition. And like this case is like definitely more interesting, but it's also a little more tedious. And this is what's going to be like related to Shor's algorithm. But I think this is a good place to start for now. And it's pretty neat to see the connection to the Hadamard transform. Okay, so our object in question is Boolean functions. And this is something that maps bit strings of length n to like this 0, 1 domain. But we're going to consider like not this type of Boolean function, but rather Boolean functions that go to plus minus 1. And these two notions are equivalent. Essentially, like if you have some normal Boolean function that goes to 0, 1, you can always convert this thing, like f of x, into a little f of x, which goes to plus minus 1, and the action of this is just negative 1 to the power of f of x. And what happens is like, in this case, addition mod 2 becomes like multiplication in this case. So that's pretty neat. And this is what we're going to focus on because, as we know from previous videos, like there's a very nice way to encode Boolean functions into the actual signs of like the amplitudes of a quantum state. And signs, of course, take on the value plus minus 1. So it's pretty neat to be able to talk about functions this way. And another like mental perspective that we should take is to be able to think of functions as vectors and vectors as functions. So there's like a very easy way to do that, in particular with Boolean functions. You can imagine just like taking its truth table. So if we have some function little f, we can imagine like what is the value on this all 0 string, and then what is its value on the next bit string in like the standard ordering, and so on. And this sort of is like the truth table of this Boolean function. And now we just put brackets around it and we can just start calling it a vector. So this lives in a space that's like the complex numbers to the 2 to the little n. I mean, it's not like the full complex numbers because this only takes on plus minus 1 values, but like the idea is it's a 2 to the n dimensional vector. And like this whole notion of a vector is like entirely equivalent to thinking of it as a function. But it's nice because now we get to like throw linear algebra at this problem and make sense of like what this discrete Fourier transform is really doing. So the discrete Fourier transform is like an operation that you can apply to a vector or a function or any like sequence of numbers that sort of decomposes it into different functions that tell you something about like the underlying patterns of your initial vector. And what it is in like a linear algebra sense is a unitary transformation. So it's like a rotation. So you can imagine like you have some vector in a 2-dimensional space, which we'll call V. And this thing has like coefficients in the standard basis, which are like these points over here. But what a unitary transformation does is it like picks out another orthonormal basis. So these are perpendicular. And it sort of just gives you V in terms of this new basis. So you need to find like this magnitude and like this magnitude here. So this is like the projection of V onto your new basis vectors, which we'll call E1 and E2. And if this is a unitary transformation, then E1 and E2 are orthonormal. So like the dot product of the two is 0. And essentially this is like exactly what the discrete Fourier transform is doing. But the basis with which we transform to is going to be like particularly interesting in the context of functions. And the basis elements, we're going to call them, or we're going to denote them by the capital Greek letter chi. And each of them are indexed by like some bit string. So we need 2 to the n different chi's. Each one's a vector in a 2 to the n dimensional space, or it's like a function. So this S ranges over all possible bit strings. And they have the property that they're orthonormal. So chi of S, chi of T, like this inner product. And this is just like the standard dot product. Like if this thing were taking on complex numbers, then you have to take like complex conjugates on this side, but we're not going to worry about that for this. I mean, it's not too much to worry about anyways, but yeah, so if these things are orthonormal, then the value of this is 1 if S is equal to T, and 0 otherwise. And the idea is like each of these chi's is going to represent like a particular pattern in our data or in our vector. And we want our discrete Fourier transform to give us this function, like for any particular f, give it to us in this different basis. So express it as a linear combination of these chi of s's. And what we do is then we examine like the coefficients, like whatever term goes here, which will denote f hat of s. And if one of these coefficients is like very high, then we can sort of conclude that f was like very similar to this particular chi of s pattern. And that's like the whole idea behind this Fourier transform is like, if these are interesting enough, you can learn something like very nice about your initial Boolean function. And thinking of this in terms of like vectors, like as a unitary transformation, if we have some f, which now I'll just put a ket around because, I mean, we're halfway there. We have a vector. In order for it to be a quantum state, it just has to be normalized. And we're not going to worry about the normalization constant, but yeah, we're just going to start referring to this thing as a quantum state. So the idea is like after this QFT transformation, sub 2, because this is like over this particular group, that each of these elements or each of these coordinates is going to be like this correlation with a particular pattern. And as a result of like the unitary transformation, what you get is like each of these entries is just the inner product of some particular chi of s and our function. And chi of s is like its own Boolean function. So this inner product is like essentially just a sum over all possible input strings of f of x times chi of s of x. And now I think we're ready to like define what chi of s is, and we'll see that it's like exactly the Hadamard transform when we do this thing. So chi of s is, like I've said, a Boolean function, but here we're considering it going to plus minus 1, and its action on a particular bit string, x, is to take -1 to the power of x dot s, where this is like the inner product mod 2. So this thing is like a sum over all I, such that s of I is equal to 1, because these are the only terms that survive, of xi mod 2. And if you can recall, this is like exactly what we get in the signs when we apply the Hadamard transform to like some computational basis state. So in particular, Hadamard acting on x is this quantum state where we range over all y, or I'll call it s, of -1 to the power of x dot s of x. No, sorry, of s. So what this thing does to our function is, as we'll see, like the exact same thing that you would do if you had just applied the Hadamard transform. So let's do that and let's see like exactly what we get. So um, first, this function f, you can write it as a vector, you can write it as a sum over computational basis states, because like each computational basis state is just like a one hot vector. It's like a 1 in that particular position and 0 everywhere else. So you can just sum over all those values and express the exact same thing. So we can say this is like f of x on this particular basis state. And now if we apply f, what we get is, sorry, if we apply h onto f, we get this thing. And now we can use our formula here, and we get that the Hadamard transform on f is the following. And notice, like, this thing over here is exactly the inner product of chi of s. Like, this thing is chi of s on x. So this is the inner product of our two functions. Oh, not quite. You have to swap this thing, which you can do. So we swap the order of the sums, and this thing is the inner product. So it's f chi of s. And as we can see, this gives us like exactly what we wanted out of our Fourier transform. And the coefficients end up being this inner product. And now what we can do is say, okay, h is unitary transformation and it happens to be its own inverse. So if we apply h again to f, we just get f on the left-hand side. And then if we apply h over here, what do we get? We can just quickly calculate this. And here we're going to get a sum over -1 x dot s of x. And this thing is just chi of s. So that's like chi of s as a function or a vector. And we sort of just done our like Fourier decomposition of our initial f by making use of this Hadamard transformation. So this thing corresponds to like the f hat of s. And it's like the strength of f with respect to a particular XOR pattern. Now, like, it's fair to ask, like, what is the point of this? Like, why could this possibly be useful? And now I think it's a good time to like reminisce a little bit on what we did when we were talking about the Bernstein-Vazirani algorithm. So what Bernstein and Vazirani did was like very clever. They used this fact that you can like decompose these implicitly like implemented functions into this chi basis. And they asked a very like specific question. So in particular, if you have some Boolean function, which you know is implementing this mod 2 inner product with some hidden bit string s. So this is like unknown. Then how many calls to like some black box unitary that's going to implement f of x can you determine this hidden bit string s? And from previous videos, we know that we can use this u of f, which does this, just to remind ourselves. We know that we can use this to obtain the following state, like in one call, which I'll call psi. And psi is this state. So you can encode like the value over the entire like truth table of f of x into these signs of this like superposition. And from like the work that we just did with all of these chi's, like it should be clear that this is chi of s. So if we want to decompose like psi into this chi of s basis, when we apply h onto psi, given that it already is chi of s, um, what we get is just s with 100% probability. Due to like the orthonormality of these, all the other terms in the sum will cancel out to zero. And this was pretty much the logic that they used. Like when you were first presented with Bernstein-Bazarani's algorithm, it's like a little bit confusing how the whole thing works. But now that we see, like they were just putting this thing into a basis which it like already exists in, you can like immediately determine what this S is with one call to your oracle, which is like as opposed to the classical case, you need like n. So that was pretty interesting. But like there was this like lingering question, okay, is this ever going to be useful though? Like is there any like cuz this was like a very artificial problem, is there any problem where we can use this like similar logic and actually do something that's like interesting or useful? Um and like it was unknown for a while, and then Shor came around and like showed that the answer is yes indeed. Like you can factor integers, which is like scary for cryptography. Um, but yeah, like we'll get to that. And like the quantum Fourier transform that we're going to discuss, like in that case, is going to be over like this group, Zn with like addition. But yeah, like I thought this was like a nice like special subcase of all this to give some intuition of like where these quantum algorithms are even coming from, and like what's the deal with this whole like quantum Fourier transform stuff. Yeah, so thank you.